Hello students, and welcome to section 6.3, Vectors in the Plane. Introduction. Some quantities have both a magnitude, which we're going to define as a length, and a direction, and therefore cannot be represented by a single real number. Such quantities can be represented by a directed line segment. Examples of this will be force and velocity. And we are going to use some of these ideas in the context of physics as we continue. A directed line segment has an initial point and a terminal point. Its magnitude, and as I already said, length, denoted by PQ, can be found by using the distance formula. So I do have some depictions here for us to take a look at. First, we'll start with the drawings of PQ. First, noting that this particular vector is what we're going to define it to be, of course. A vector, PQ, starts at point P as the initial point, and it ends at point Q, the terminal point. So vector PQ starts at point P and ends at point Q, and you can see the arrow pointing to Q. There are equivalent vectors as well for us to take a look at, of which have the exact same direction and the exact same magnitude or length. So vector PQ has equivalent vectors, as you can see, these three, with the same direction and the same magnitude or length. So they're called equivalent because they have those two features. Force and velocity will, in some cases, be best represented using these vectors. Two vectors are equivalent if and only if they have the same direction and magnitude, as I already described up above. The set of all directed line segments that are equivalent to a given line segment is called a vector V in the plane. So for example 1, let V be the vector from point P, 0, 0 to Q, 4, 5, and U be the vector from R, which is 2, 3, to S, which is 6, 8. So we're going to go ahead and show that vector V is equal to vector U. There's two features, again, that we have to be mindful of as we proceed. The first, of course, again, we want the same magnitude to be part of what we're analyzing, which again is the length, but also we want the same direction. So this first example is a very kind of general example in which we'll be able to portray vector V from point P to point Q as such. We'll use actually the distance formula. Okay, and we're going to do a graph of this in a moment as well, just to give us some perspective. So from point P, 0, 0 to point Q, 4, 5, using the distance formula, as you recall, the square root of the x's subtracted is squared, so 4 minus 0 quantity squared, plus the difference in the y's, also squared. Square rooting all of that leads to this particular distance. I've also denoted vector V, noting these symbols as well. These symbols, or this symbol with every vector that we analyze, is going to be a representation of distance. So the distance from point P to Q, or vector V, the length of which, again, is noted here as such, is just that square root of 41. Similarly, we'll go ahead and do the same thing with vector U, or from point R to point S, or again, vector U, the length of which we can see here the square root of 6 minus 2 quantity squared, and then 8 minus 3 quantity squared. That also is the square root of 41. So I've checked off the fact that step 1 is essentially taken care of. Let's see step 2. Step 2 is to verify that in this particular instance, and you can start to see the graph unfold, okay, we're going to be taking a look at slopes. Okay, so vector PQ, and notice my notation. Okay, my notation is as such. So the slope M of vector PQ, again, this little denotation shows the vector PQ. You could also use vector V, I guess, as a subscript, wherein I could take the difference in the y's, 5 minus 0, divided by the difference in the x's, 4 minus 0, to get a slope of that vector PQ, or V, as I've also noted here, as such, 5/4. So that's the slope. Similarly with the vector rs, or in other words vector u, and again notice I've plotted my 2 points with the arrow pointing to the terminal point. So from R to S and from P to Q. So the direction and the length better end up being the same. And as you can see, the slope is exactly the same as the other slopes. In other words, 8 minus 3 divided by 6 minus 2 using the slope formula. That checks that box, so to speak. So yes, same magnitude, same direction. Vector v is equal to vector u. Again, both of these have to be true, which they are. And we move forward and start to use a little bit different notation as we continue. So, component form of a vector. A vector is in standard position if its initial point is at the origin, so 0, 0. Also, if v, vector v, is in standard position and its terminal point is v sub 1, v sub 2, then v can be uniquely represented as follows. So vector v in the component form with these bracket-looking notations, v1, v2. This is called a component form of vector v. Furthermore, if v is the vector from x1, y1 to x2, y2, then its component form would simply be the difference in x's, comma, the difference in y's. And we actually saw that with the first example, as I'll uncover yet again. So for example, remember in example 1, when we took 4 minus 0 and 5 minus 0, technically we did that in the context of the distance formula, but actually that then should have lent to the following component form. So in the prior example, just to reflect a little bit, 4, 5 for vector PQ, 4, 5, this ordered pair, is a representation of PQ. Vector PQ can be written as such. So we need to keep that in mind as we're continuing. The same goes with vector RS. In other words, 6 minus 2, 8 minus 3, which should end up being the exact same component form. Even though vector RS is not technically starting at the origin, right? We can see that vector RS is sitting up above the x and to the right of the y-axis, the x-axis and the y-axis. The point R is not at the origin, but we can essentially describe this as the same vector. It's an equivalent vector. It is not in standard position, however, so when you move, if you can imagine moving vector RS such that R is at point P and S is at point Q, it then will change to this form. Okay, so we do need to have an understanding as to how we can find the component form. The answer, of course, is the same because they're equivalent vectors. Please be mindful of how to rewrite it in standard position and in this component form. The magnitude or length of v, as you can again remember me writing it as such, is simply the distance formula. And if x sub 2 minus x sub 1 is also from back here the way we write the v sub 1, and similarly y sub 2 minus y sub 1 is how we write v sub 2, then you can easily just describe the component form v1, v2 as such, the square root of v1 squared plus v2 squared. And in the context of, again, finding the distance or length of PQ and RS, you can simply plug in 4 here, 5 there, and do the square root to end up with your length of that particular vector. PQ and RS will end up being the same length. Note, a unit vector has a magnitude of 1. If in fact you're going to write that in the notation as we've described, looking at the vector v length, it's equal to 1. That's what we call a unit vector. A zero vector, 0 has a magnitude of 0. So the same basic idea applies. And as you can see, you actually can rewrite it as a component form as such, 0, 0. So it's literally just the point right at the origin on the xy axis. To just describe example 1 in a little bit of a different manner, using u in specific terms, as you can see, literally using the language though of terminal minus initial. So vector u on example 1 simply is a matter of subtracting terminal minus initial, x2 minus x1, comma, terminal minus initial y2 minus y1, which is going to be imperative when we take a look at starting the process of finding the component form and or the magnitude of a vector, which we're about to see in the next example. Find the component form and the magnitude of the vector from 2, -4 to 5, 7. I labeled this as P and I labeled that as Q. So if we see here, going through the process of finding vector PQ, take a look, I'll uncover here. So vector PQ, in other words vector V, it's simply a matter of, as I'll scroll back up above, taking the difference in the x's, but be careful, we're doing terminal minus initial. So instead of 2 minus 5, it's 5 minus 2, and the reason is because Q is the terminal point. So 5 minus 2, comma, 7 minus -4, as you can see with those two representations, v sub 1, v sub 2. 5 minus 2, of course, is 3. 7 minus a -4, or 7 plus 4, of course, is 11. So that's how you'll represent this. Be careful. If you subtract 2 minus 5, you will not get the appropriate value for v sub 1, nor -4 minus 7 for v sub 2. As such, as we continue, it is worthwhile, I believe, taking a look at the graph. So again, keeping in mind the distance, or the magnitude, pardon, which is essentially the distance formula of vector v. Notice my notation. So this is just describing the component form. It's like an ordered pair if you think about it. But now we're going to go ahead and use the distance formula, or at least similar to the distance formula in context. Once you've established the component form, the distance formula is as easy as v1 squared plus v2 squared, and then taking the square root of that. And in this particular case, that's simply the square root of 130. Okay, some roots you will have to simplify. In this case, that's perfectly good. The graph, let's take a look. As far as the graph goes, keeping in mind point P, which was your initial point here, and point Q, your terminal point. So this is the vector that we started with. However, this vector is not in standard position, while this vector V is. These are equivalent vectors. Again, they have the same direction and they have the same length or magnitude, same thing. But the nice thing about vector V now is that it starts at 0, 0, and all you have to do to finish drawing this, so to speak, or putting it together and making connections as such, is label what? 3, 11 as the second point, and therefore vector V, you could do your analysis just as any other problem goes. With it being in standard position, you can do various applications, including trigonometry, which we'll be doing later. Using vector V, though, in blue will be more advantageous in most instances. All right, so vector operations. Let's continue. Two basic vector operations are vector addition and scalar multiplication. Geometrically, u plus v is the vector formed by the initial point of u and the terminal point of v. When the initial point of v is placed at the terminal point of u. Now I went ahead and I drew a picture for the sake of efficiency. Here's a picture, noting that u is a vector in this direction and with that length, and v is another vector, as you can see. So if I were to ask you to add vector u plus vector v, the idea is you need to place the initial point of one to touch the terminal point of the other. So geometrically speaking, and there is something to be said about, as you're seeing here now, called the parallelogram law. The parallelogram law takes vector u and vector v such that the initial of one touches the terminal of the other and vice versa. So this point, as you can see, head to tail, so to speak, head to tail, where the red vector and blue vector come together. The green vector is the answer or resultant. So u plus v is the resultant vector, we call it. Now you could also put the red vector on this side and then the blue vector over here, but look, the green vector is still the same exact answer. It points in that exact manner, noting that the arrow points to where the blue vector is finishing in that particular picture, and on the other side where the red vector finishes. The parallelogram law is very clearly justifiable. We'll leave off there and continue at another time.